Electricity is notoriously hard to wrap your head around, mainly because you can't actually see it moving through a wire. Voltage acts exactly like water pressure. It's the driving force pushing everything forward. The resulting flow is current, the actual movement of electrical charge traveling through the system. If we squeeze the pipe, the flow visibly slows down. That physical restriction is resistance. Every basic electrical circuit you will ever encounter is just a balancing act between these three variables: a push, a flow, and a restriction. In the 1820s, a physicist named George Ohm decided to move past analogies and started measuring these forces in a lab. Mapping a basic circuit, he noticed a strict pattern. Doubling voltage doubles the current. They are directly proportional. Factoring in resistance as a constant, he created an exact equation. Voltage equals current multiplied by resistance. We measure these in volts, amps, and ohms. There is a strict physical limit to this math. The variables only stay perfectly proportional if the temperature of the wire remains completely constant. This animated diagram shows the Ohm's law triangle. Moving algebraic terms around causes mistakes, so this bypasses algebra entirely. To use it, simply cover the variable you're trying to find. The remaining letters show exactly what to calculate. Let's look at this circuit schematic. We have a current of 2 amps flowing through a 5 ohm resistor, and we need to find total voltage. Looking at our triangle, we cover the V, then multiply 2 amps by 5 ohms to get 10 volts. The visual layout guarantees you will always set the formula up correctly, whatever variable is missing. Here is a new circuit with a 12-volt battery and a 4 ohm resistor. Pause the video and use the triangle to find the current. To find I, divide voltage on top by resistance on the bottom. 12 divided by 4 gives us 3 amps. Now, remember that rule for earlier about the temperature having to stay constant? Let's look at what happens when it doesn't. Inside this incandescent light bulb, the metal filament gets intensely hot while generating light. That massive heat violently increases the resistance, breaking the proportional math entirely. Ohm's law is highly reliable, but it's an empirical rule, not a universal force like gravity. It only applies strictly to materials that maintain a stable temperature. This diagram shows two parallel scenarios. Circuit A and Circuit B both run on a 10-volt battery, but Circuit A has a 2 ohm resistor, while B has a 5 ohm resistor. Without doing the math first, look at the restrictions and decide which one allows more current to flow. Calculating them out proves the intuition. Circuit A pushes 5 amps, while the higher resistance in Circuit B chokes the flow down to just 2 amps. When you lock your voltage in place, raising the resistance will inevitably crush the current. This graphic summarizes everything we've covered. You have the calculation triangle, the formulas derived from it, and the crucial rule regarding temperature. Conceptually, voltage pushes, resistance slows, and current flows. Grab a screenshot of this frame. Once you commit this relationship to memory, you have the exact framework needed to decode any basic electrical circuit.